అది తెలియదు మా రాజుగారికి అందులో చేస్తున్నాం ఇప్పుడు అది అంతేనా 700 రూపాయలు ఇప్పుడు ఇది ట్రాన్స్ఫర్ చేస్తుంది మా ఫ్యామిలీ.
So let me start with the second class on solid state. And if you can recollect what we have done in the first class, we have seen the different types of crystal systems. Yes, the different types of crystalline and the amorphous solids. And what are the different types of crystalline solids we have seen? Ionic solids, metallic solids, covalent solids, and molecular solids. In molecular solids, what have we seen? Non-polar, polar, and hydrogen bonded. You can remember. First, we have seen what is the difference between a solid, liquid, and a gas. Then we went with types of crystalline solids. So in types of crystalline solids, what did we see? One is molecular solids. Yes. In molecular solids, we have seen 3 different types. Then we went with ionic solids, metallic solids, and covalent solids. Then we went with different types of crystalline systems. You can recollect what we have used, how to remember it. Crazy teachers made us to draw triangles, hexagons, and rhombus. So this is the way you will remember. And what do these 7 different types of crystal systems give us? They give us the relation between A, B, and C, which we call it as axial distances. Sometimes we also go with using a what is called as the edge lengths, and we also go with the relations between the angles alpha, beta, and the gamma. So depending on the edge lengths and the angles, we have the different, how many types of crystal systems? 7 types of crystal systems. Then these crystal systems are arranged in further types. Let us see how they are arranged. And if you can remember what is an unit cell, it is the simplest arrangement, 3-dimensional arrangement of the crystal lattice, which will set the complete pattern of crystal. We call it as a unit cell. So if I take a basic unit cell like this, which is a simple cube. So if I take this, depending on the positions, like these positions, we'll have it as corners, and we also have, these would be the corners. Hope you can see. I meant having lattice points only at the corners. So you can understand these positions are the corners. So if we have the lattice points, what are lattice points? Whatever is the compound made up of. Like if it is an ionic compound, these are lattice points are the positions of the ions. Lattice points are what we call it as the constituent particles. It can be ions, molecules, atoms, or anything. So if the lattice points are present at the corners, we call that as simple, primitive, or a basic unit cell. So if you go for any unit cell, remember எல்லா unit cellக்கும் cornerல lattice point இருக்கும். So we will have a lattice point. What is a lattice point? Anything. If it is an ionic compound, it will be ions. If it is a particular solid, it will be molecules. If it is an atom, like carbon, graphite, or the diamond, you will have the lattice points like the carbon particles. So in a simple crystal system, we'll have lattice points only at the corners. And along with the corners, we will also have certain lattice points at the faces. When this is a face, this whole thing is a face. So if we have certain lattice points at the center of the face, along with the corners, we will call it as a face-centered cubic lattice. That is, in a unit cell, along with the corner lattice points, if we have center of each face along with the corner. So you will have to remember, along with the corner, we will have at the center of the face. What do we call that unit cell as? Face-centered cubic lattice. Short form will be FCC. So simple or the primitive or the basic unit cell will have lattice points only at the corners. How many corners will a simple cube will have is 8. So 8 corners. So if I take a simple cube, there will be 8 corners, and at the 8 positions you can find the lattice points. If I take a face centered, there will be 6 faces. This is 1, this would be 2, this would be 3, this would be 4. 1 above and 1 below, I can say 6. So there will be 6 faces if I take a simple cube. So along with the corner, the lattice points will also be present at the 6 faces. Then in case if it is a body centered, where do we have the lattice points? Along the corners you will also have. So in all the different types of crystal systems that we are taking, always you will have at the corners. So along the corners, if you have it at the center of each face, you call it as FCC. With the corners, if there is one lattice point at the center of the body, center of body of the unit cell, we call it as body centered cubic lattice. A unit cell having a lattice point at the center of the body as well as that of the corner, we call it as body centered cubic lattice. So how do we write that? BCC. N-centered is along with the corners, there will be only 2 opposite faces. Though out of 6, it will be any 2 opposite faces if the lattice points are present. We call it as N-centered. In N-centered, there are lattice points in the face centers of only 1 set of faces. So any 2 opposite faces. Out of 6, it can be any 2. Like again, let me go over the simple structure of this. It can be either at these 2 positions, or it can be at these 2 positions, or one up and one below. So it can be any 2. What is the basic difference between face centered and an end centered? In face centered, you find along all the faces, while in the end center you find only at 2 opposite faces. Puriyudama? Any doubt? Shall I continue, or if you have any doubt, do ask. So what are the different types of simple crystal systems that we have is primitive, wherein the lattice points are present at the corners, face centered along with the corners at the center of the faces, body centered corner along also at the center of the body, and end center will be along with corner, will have it at two opposite faces. Now this each crystal system that we have seen, the 7, is further having different crystal systems like primitive, body centered and the face centered. Let us, if I take a simple cube wherein the edge lengths are equal, A equal to B equal to C, and if I take the interaxial angles, even the angles we have taken. So these crystal systems will have further different types of arrangements that we have seen. So cubic will have primitive in the sense it will have only at the corners. We'll also have a type of body center, that is along with the corner you will have a lattice point at the center of the body. If it is face center, corner with the center of each face. Then again tetragonal, if you take, again it has two different crystal systems, primitive and body center. Likewise, all the 7 crystal systems further have different lattice arrangements, totally giving us 14 different types of crystal systems. And these further 7 different types of crystal system into different arrangements, lattice arrangements, we call it as Bravais lattices. These 14 different arrangements of lattice based on the 7 basic crystal systems, we call it as Bravais lattices. If you go with cubic, we have primitive, body centered, face centered. If we go with tetragonal, we have primitive, body centered. Orthorhombic will have primitive, body centered, face centered and end centered. Monoclinic will have primitive and end centers. Triclinic, hexagonal and rhombohedral will have the primitive type. So these 14 different arrangements, we call it as, these 14 different types, we call it as Bravais lattices. Okay, this is the way it has been shown. If you can see it very clearly, what are the different types of crystal system? Primitive, as I was telling you, you will have the lattice points only at the corners. Hope you can see that. You have crystal systems at the corners. In this crystal system, you will have the lattice points only at the primitive or a simple unit cell. So in case of body centered, we'll have at the corners and one at the center of the body. You can see that. Let me use a different color and show you. If you can see it, see, this is the one which is at the center of the body, center of body of the unit cell. And if you go with face centered, this is one face center, this is one face center, this is the one, the face centered, you can see one at the face center. And these are the ones which you will have to visualize, one at up and one below. All these would be at the corners. These are the corner ones. Yes, all the remaining would be face centered. So in body centered, what do we have? Corner plus body centered In face center, we'll have corner plus center of face. In case of primitive, we only have it along the corners. Hope this part is clear. Faces for FCC and BCC. See, this is body centered. Right? Why do we call it as body centered? Is because there is one unit cell at the center of the body. See, faces will remain same whether we take a body centered or a face centered. This is one face. Okay, let me put this is one face. This is 2. This is 3. This is 4. One will be up. One will be down. I mean, let me take a room. You take a simple basic room, whether it is a room which is rectangle, a room which is square, you can see 2 on opposite sides and one as the cellar and one as the floor. So here 4 you can easily see, one up and one below you will have to visualize. Whether it is body centered or the face centered, you will have 6 faces. Whether it is body centered, face centered or a primitive, if I take a simple cube or any other 3-dimensional arrangement, it will have 6 faces. But when do we call it as a face centered? Is when there is a lattice point at the center of the face. When do we call it as body centered? Is we have lattice, though there are faces, you will have a crystal lattice only at the center of the body. Maithili, is it clear, ma'am? Maithili? Okay. Shall I continue? See, I'll just put it again for your understanding. I'll remove all this and then. See, Maithili, I'll show it in the primitive because there are no unit cells. See, this is one phase. This is second phase. This is third. This is fourth. Here you will have to visualize 2, one up and below. So I can put 5th and 6th here itself. These are the 6 phases, whether irrespective of whether it is primitive, body or the face centered. You call it as body centered when you have lattice points as in primitive. Along with that we have one at the center of the body. In case of a face centered, along with the corners we will also have it along all the faces that I have marked. So the basic difference of body centered and face centered is purely based on the lattice points. Thank you. So let me proceed further. Again, primitive is shown when we are taking tetragonal. In if you can look at the first one that I have shown, wherein all the sides are equal, A equal to B equal to C. This is when we are taking up a cubic crystal, the first type, which has primitive, body centered and the face centered. Now if you go for tetragonal, you can see one of the side is different from the other 2 sides. Yes, one side is different in length to that of other. 2 angles between faces all are 90 degrees. Alpha equal to beta equal to gamma is equal to 90 degrees, but one of the edge length is different. What are the different types you can see is primitive and body centered. What is body centered? Along with the corners we have a crystal, one more lattice at the center of the body. So let us see all the 7 different types of arrangement with what are the different lattice arrangements that we have. So in tetragonal we have 2, one is primitive and the other is body centered. Now if you go for orthorhombic, with unequal sides and angles. How many are we getting? Primitive end-centered. If you remember, I said you will have two lattice points on any of the opposite faces. These are the two opposite faces. You can see two. It can also be these two opposite faces. It's easy for visualization when we go for this. இந்த two sides இருக்கலாம், இல்லன்னா மேல ஒன்னும் கீழ ஒன்னும் இருக்கலாம். We call it as end-centered. Then body-centered, inga theriyudilla, center of the body. We have all faces to this. There is one at the center of the body. Then face centered, inga theriyudilla. 1, 2, 3, 4, 5 and 6. 6 phases. These two you will have to see, one up and one below. So what are these? 4 different types of orthorhombic lattices. See whether it is primitive, body centered, face centered or end centered. The only difference that we are doing in these crystal systems is we are trying to change the edge lengths and the angles. எல்லாம் கிளியரா இருக்குல்ல? புரியுதா? நமக்கு சிம்பிள் இல்லனா பாடி சென்டர்ட் ஃபேஸ் சென்டர்ஸ்ல டிஃபரன்ஸ் என்ன இருக்கும்? பாடி சென்டர்ல will have one extra crystal lattice at the center of the body along with the corners. அதே ஃபேஸ் சென்டர் பார்த்தோம்னா corners along with corners will also have one at the face center. Summed along all the faces. End center la rendu mattum da irukum, edavadhu rendu opposite faces. இந்த ரெண்டு opposite faces இருக்கலாம், இந்த ரெண்டு இருக்கலாம், இல்ல மேல ஒண்ணு கீழ ஒண்ணு இருக்கலாம். Fine. Let's continue. Then monoclinic வந்து எவ்வளவு டைப் இருக்கு நம்மளுக்கு? எல்லா unequal sides. Two faces have angles different to 90 degrees. The angles are shown. என்ன types இருக்கு? Primitive and end centers. Angles பாத்தீங்கன்னா இங்க இந்த ஆங்கிளும் different இருக்கு. The same thing. இந்த angle different இருக்கு. Have different angles. So what are the different types? Primitive and end center. So these are the different, you can see the different types of crystal systems. Maximum possible number of 3-dimensional lattices that we are seeing. I mean the question is with respect to Bravais lattices. எவ்வளவு Bravais lattices இருக்கு? Crystal systems வந்து 7. What are the different Bravais lattices? Mind the question parma, maximum possible number of 3-dimensional lattices are. So how many different types of 3-dimensional lattices will have us? 14 types. Right? The 14 types we have seen, that is every type is further divided into simple, end-centered, body-centered, face-centered depending on what are the different types. Which of the following crystal structures will have end-centered lattice arrangements possible? So we have seen what is end-centered is when you have the lattice points along two of the opposite faces. எதுல இருக்கும்? ஆர்த்தோரோம்பிக்ல இருக்கும், மோனோக்ளினிக்ல இருக்கும். So it's both 2 and 3. Good. So let's see how these arrangements are. So first, if you can see, it is a simple Unit cell, the unit cell, what is the smallest part of three-dimensional crystal lattice, which will set the complete pattern. If you can see that the simple one is arranging itself to form the complete point is shaped equally by 8 unit cells. So if it is shaped by 8 unit cells, what will be the contribution for that unit cell? So contribution for that unit cell will be 8 into 1 by 8, which is equal to 1. Just understand this calculation, then we can see the three-dimensional element. With the picturization, we can see that. See, this is one that is present at the corner. You take a simple cube over here, you will understand it's a corner. But this is equally shaded in a three-dimensional crystal arrangement, shaded by 8 other unit cells. When a lattice point is present at the center of the body, it cannot be shaded by any other unit cell. So the contribution for an atom at body center will be equal to 1, because this cannot be shaded by any other unit cell. Hope you understand. Contribution of an atom at face center. So let me consider this as a face center. It's almost like a wall. Wall is common between two different rooms. If I consider in that way as two different rooms, so this face is common to two different cells. So what will be the contribution per unit cell is only half. This will get half, this will get half. How many face centers are there in a cube? Are 6. Contribution of atom per unit cell is equal to 6 into 1 by 2, which is equal to 3. Whatever calculation I have shown it, just look at the picturization of it as one. You can easily understand. I have shown the calculation. If you say you have understood, I'll just go with the next slide so that you can have a clear look at the picturization. ரொம்ப நல்லா புரியும். Calculation பார்த்துட்டு அதுக்கப்புறம் picturization பார்த்தா நல்லா clear-ஆ இருக்கும். So in simple cube, what are we getting? So you can see for the simple cube, how many are we getting? Only 1. So let's go with the next one. Number of atoms in a unit cell of BCC. In BCC we have at the corners will contribute 1. These are at the corners, and at the body center there is one which is not shared by anything. Here there is a sharing, here there is no sharing. So total lattice points in a BCC crystal cubic crystalline structure will be equal to 2. So let's also see how we are getting it as 2. Center you can see it as 1. Let's see how this whole thing is making into 1. You have seen in the previous picturization wherein the corners are making up 1. So let's also see how we are getting 2 for BCC. Okay, number of atoms in an FCCs. In FCC we have, where do we have? Corners plus faces. Corners is 8 into 1 by 8, contribution will be equal to 1. Faces is 6 into 1 by 2, which is equal to 3. So total how many are we getting? 3 plus 1, 4. So the effective number of atoms in a unit cell of FCC will be equal to 4. Let's also look at the picturization of it. Any doubts? The doubt will come. So let's visualize this, how we are getting it a face center. The yellow dots are the ones, or yellow are the lattice points at the corners. See, these yellow ones are the center of the faces and the blue ones are the corners. So you can visualize how the face centered. If you remember in the first class I said, how are we getting the three-dimensional picture? Here you can see they are all so closely placed. See, corner is made into 1 and the face centered is made into 3. Just have a look once again. Right, the number of FCC we are getting it as. So just have a look once again at BCC also and the simple, so that we can so in a simple cube we are getting 1 lattice point per unit cell. So you are able to understand how we are getting 1 whenever we have the lattice points at the corners in a simple cube. So the contribution of atoms in simple cube is 1. Let's go to BCC once again and see. BCC it should be 2. 1 contribution from the corners and 1 from the body center. Let's see how we are getting it as 2. Such a nice visualization where we can easily know that the number of lattice points in BCC are 2. A beautiful way of visualization. Right. Let's also see FCC after this. Let's go for FCC and see the visualization how we are getting it as 4. Right. Let's go with what will be the contribution at an edge center. So if I go with a simple cube, again, This we call it as an edge center. This we call it as an edge center. The contribution to that, how many edge centers will be there? There will be 12 edge centers will be present for a simple cube. The contribution per unit cell is 1,4. That's what has been shown here, which will make a total of 3 lattice points in case if the lattice points are present at the edge centers. Ella puriyadillamma. Visualization, if you see, it's very clear. So far clear? Shall I go on? Okay, let's see how we calculate the density of a solid substance having a molar mass of m, and it is generally done by X-ray diffraction method. Edge length is generally, though we have taken A, B and C, we generally go for representing it as A. So let's calculate the density of the different crystal systems. How do we write when there is, okay, volume of the unit cell will be equal to the cube of the edge length. A cube is the volume of the unit cell. Number of atoms in unit cell will give us the effective number of atoms. Now, what do I mean by effective number of atoms here? If I take FCC, I'll make, due to phase center, there are 3 lattice points, and at the corner it is 1, a total of 4. If I take a BCC, I'll have 1 contribution at the corner and 1 at the center of the body equal to 2. If I take a simple cube, we'll have equal to 1. This is the effective number of atoms, the calculation that we have seen in the previous slides. That will be different for the different unit cells. And m as the mass. In case if it is an element, we will take the atomic mass. In case if it is a compound, you will take the molecular mass. That will give us the mass of an unit cell. Then we know density, okay fine, let's go with that later. Mass of an atom present in a unit cell, when we will find the mass of a single one, we will have to divide that by an Avogadro number. This mass that we get it is divided by the Avogadro number. Again, m is molar mass in case if it is a compound. If it is an element, it will be an atomic mass. Density we know as mass by volume. How do we get mass? Z into m. What is Z? Z is the effective number of atoms into mass divided by Avogadro number will give us what is mass of unit cell. And what is the volume of unit cell is A cube. So this formula gives us how to calculate the density. This is constant. The only thing that we have a constant is Avogadro number. What is that? 6.022 into 10 power 23. Let's see few calculations on the density. Fine. X-ray diffraction studies show that copper, it's a metal atom, crystallizes in an FCC unit cell. The moment you see it as an FCC unit cell, what you will take? Z, you will take it as 4. Unit cell with an edge length of 3.608 into 10 power minus 8 centimeters. What is that? A is equal to 3.608 into 10 power minus 8 centimeter. In a separate experiment, copper is determined to have a density of 8.92 grams. Calculate the atomic mass of it. How do we take? Density is equal to Z into M by Avogadro number into A cube. We know D, we know Z. Z you will have to take up based on what the unit cell is, what we will have to calculate as M. So substitute, let's substitute and see what we will get. That is 4 atoms. So let's see what are we going to get. See, density is, so what do we need as mass? So density, mass would be equal to density into A cube into Avogadro number by the Z. That's what is substituted here. Density is 8.92 grams per cc. Avogadro number is a constant 6.022 to 10 power 23 atoms per mole, and this will give us the volume A cube 3.602 into 10 power minus 8 centimeter cube by number of atoms is 4. So if we calculate this, what are we getting the answer as? 63.1. So this part of it is important for both your NEET exam as well as your board exams as well. It's a very simple thing. The only thing is you will have to take care when you are calculating. Otherwise, it's a simple, very simple calculation. Puriyardama. Polama next slide. Fine. Okay. Silver forms. CCP lattice and X-ray studies of its crystal show that the edge length of the unit cell is 408 picometers. So CCP you will take as face centered crystal lattice. That will become 4. It's given in picometers. You will have to convert into centimeters. 408.6 into 10 power minus 12 meters. What will that be equal to into centimeter? 408.6 into 10 power minus 10 centimeter. Because it's given in picometers, generally they give you in picometers, angstroms, nanometer. You will have to see based on what options are given. If it is given in cc, you will see that you convert them into centimeters. Calculate the density of silver atom. D is equal to Z into M by Na into A cube. Calculation பண்ணலாம் அம்மா. So whenever they give you CCP, you understand it is the FCC that is given. That is 4. Here it's given in meters. Let's convert that also into centimeters. 408.6 into 10 power minus 10 centimeters. The answer that we have got it is in kgs per meter cube. Will also be equal to your grams per cc. One way you can do it, substitute in the direct way. Here the mass is in terms of grams. If you convert that to kgs, you can retain this in meters. 1 kg per meter cube is equal to 1 gram per cc. So you can either take it converting the mass to kgs and then and the distance you can maintain it as in meters, or retain the mass in grams. Grams la vechittu idu vandu centimeters la change pannum. So you will make it into 408.6 into 10 power minus 10 centimeter cube. In either way, since 1 kg per meter cube is equal to 1 gram per cc, you can get this. Yeah, any doubts? Any doubts in this part so that I can just go with that? Any slide that you did not understand so that I can give a quick recap? Any doubts more? Because these are the calculations which we will have to use it further in our classes, meant the effective number of atoms. If you understand, the rest of the thing is very, very simple. The contribution of everything. I'll just go with that again. At the corner, there will be 8 lattice points. That's what is shown here. It is equally shared by 8 unit cells. So the contribution per unit cell will be equal to 1. So whenever we get corner, the contribution will be 1. When it is at face centered, it will be 3. Body centered equal to 1, and edge center will be equal to 3. Now how are we getting this? How many lattice points do you find at the corners? The number of lattice points I have written, the effective number of atoms. At the corner it would be 8 lattice points. Face centers would be 6. Body centered would be 1. Once we have it at the center of the body, it is not equally shared by anything. Edge centers will be 12, shared by 4 unit cells. Any doubts you can ask me so that I can go with that. Otherwise, I'll just go with a quick recap of what we have done. This is 1 at the body center, which is not shared by any other unit cell. Face centered, you can see it is face center. Just visualize it as the center of 2 rooms. The wall that divides 2 rooms will be a face center, or a roof for 1 room will be a floor for the other room. So if we have a lattice point at that, it will become center of each face. It's easy when you visualize it as a room and then go for it. Or look at these videos once again, you will understand it. Let me again go for a quick recap of the visualization of all these. So simple cube, we are getting 1 lattice point per unit cell. So 1/8 of it, when we combine 8 times, see the way how many times it's rotating and then making up 8. Two, 3, 4, 5, 6, 7, 8. So 8 pieces have become 1. So just remember the contribution per unit cell is 1/8. Then in body centered, along with the corners, we have it at the center of the body. The pink color is the one at the center of the body, the blue ones are at the corners. Again, 8 small pieces at the corners is making up 1. Already at the center of the body we had 1. So a total of 2. Okay, let's take an FCC. What is FCC? Wherein you have at the corners and at the center of the faces. Let's see how we are getting it in the visualization. At the corner, it's 8 such small pieces making up one. At the face center, it's 2 pieces which are making up one. So in face center, we have 3 at the face center and 1 at the corner. Fine. It's easy. At center, you can look at the way it has been done. It is 1/4 contribution. Then, how do we calculate the density? Density is given by mass of unit cell by volume of the unit cell. How do we give the volume of unit cell? It's A cube. What is A cube? Edge length is given as A instead of A, B and C that we have seen in the first class. Instead of, we will just replace it by only 1. We will use in further classes as A. A cube will give us the volume of the unit cell. How do I get the mass of unit cell? Effective number of atoms into the mass. I want it for one single atom. So what do I do is divide it by the Avogadro number. Otherwise I'll get it for 1 mole of it. So now I'm calculating it for 1 atom or 1 molecule. How do I get that? When I divide it by Avogadro number. Any doubt in the calculation part and how to substitute and everything? Calculations of density, you can do it, right? It might take a little time for you to calculate, but once you know how to interconvert it, it will be easy to go with the calculations of density. So in some questions you can see that as an FCC, in some questions you can see that as FCCP in general. In case if this crystal structure is given as a BCC unit cell, what is the basic difference that you will do? So இதே question instead of FCC நம்மளுக்கு BCC and கொடுத்தா என்ன பண்ணணும்? என்ன change பண்ணணும்? Only thing is the effective number of atoms வந்து மாத்தணும். BCC level எடுக்கணும், you will have to take 2. Because it's given as FCC, we have taken it as 4. In case if it is given as BCC, நம்ம என்ன change பண்ணணும்? இது மட்டும் change பண்ணணும். We will have to take it as 2. Right? The general one that will be most questions they concentrate on FCC. You will have some questions asked on BCC. Simple cube ரொம்ப rare வரும். Then we have the CCP. See, either if it is given as CCP or an FCC, we will have to consider that as an FCC with an effective number of atoms as 4. So, any doubts? Just work out. First, do your NCERT textbook completely. Work out the examples that are given on density so that it will become much easier when we go with the topics. By the time we meet tomorrow, I want you to finish off all the density questions. Textbook reading, your textbook is very, very important. NCERT textbook, you just read every line of the NCERT textbook so far whatever we have done. First help should be from the NCERT, that is reading every line from the NCERT, because you can see few questions for the NEET exam or any competitive exam, they are taken directly from the textbook. So shall we meet any, I think there are no further doubts on this topic. Let's meet tomorrow at the same time.
Yeah.